All right, so today we want to talk about curve sketching, and we're going to look at this graphically today. We're not going to look at any algebraic equations. We are in the future, but for now, just how we could take a curve, how we can modify that to tell us, well, let's just see what we're doing here. So the goal is we're going to be given a function. In this case, to start with, we're going to be looking at the graph of f of x, and we're going to tell some things from it. But in order to do that, we just need some basic information here. And this is most of the stuff that we have with curve sketching that you're going to be asked about. There's maybe one more thing called a point of inflection, which we'll get to. It's not super difficult either. But all of these facts, though, apply to the original function. Okay? They apply to the original function. So the graph of y equals f of x is, and we can tell all these things from the derivative and second derivative. It is increasing if f prime is greater than 0. That should make sense, right? F prime is the slope, right? If the slope is positive, would it have to be increasing? Sure. If f prime is less than 0, it's decreasing. It's downhill. Okay. Now, when the slope changes from positive to negative, we get a maximum, a local maximum, correct? So that's when it's a maximum if f prime, which is the slope, goes from positive to negative, right? You're going uphill, you start going downhill, you had to reach a local maximum, right? And that just means that in that area, in some restricted area, that's the highest point. It's like there's a highest point in the state of Florida. It's not, it's not Mount McKinley. It's like 300 feet high, but it's still the highest point in Florida. It's still a local maximum, even though it's not very high. It's a minimum if f prime goes from negative to positive, right? You have a negative slope, you have a positive slope, you must have a minimum down there. Okay? And then the next thing we talk about is for the second derivative. Is the curve is concave up where f double prime is greater than 0. And concave is just like, it looks like this, right? The parabola y equals x squared is concave up everywhere. Okay. And if the second derivative is negative, it's concave down. We know what concave looks like, right? Concave up, concave down. So I always think a kind of a function that I know all kinds of stuff about, let's just run it through this process. Well, we'll look graphically. We'll look at the equations later on. But you can think about a parabola, right? We know that if you think about its slopes, before we look at one, so we can do this graphically. If we have a parabola, let's say it looks like this, and right, this is our original function, right? Now we know that from negative infinity to 0, it has a negative slope, correct? Right. Now, if you think about what its derivative would look like, I don't want to, it would look something, I guess I moved it, but it would look like this. It would be a line, correct? So here, if we look at the derivative graph, we see the derivative graph is negative over here, correct? Which means the original graph must be decreasing until you get to where x is 0. Okay. If we look over here to the right of 0, the derivative graph is positive, correct? It means the original function must be increasing to the right of 0. Here, this is the derivative graph. We see it's negative and it switches to positive. At 0 is where it switches, right? And then we see that when x equals 0 on the original function that we have a minimum. Right? It goes from negative to positive. The first derivative goes from negative to positive. If you think about the second derivative of this line, it would just be, this would be y equals f double prime of x. That would just be a horizontal line with some positive value, correct? Well, if f double prime is positive for all points, it means this must be concave up everywhere. Which it is, right? I mean, it's hard. It's tougher to be more concave up than to be a parabola that opens up. Okay, so for our first example on the worksheet here, we have a graph that looks something like this. Again, watch your scale here. This is 1. This is -1. So with this one, this is the most important thing to do here. This is very similar to when we did position, velocity, acceleration, is you have to identify which graph am I looking at. Right? In this case, we're given the graph of f, the original function. Right? On the back of the page, we're given the graph of f prime, which is different. Right? That's the derivative function. So what we're going to do here is we're going to create a number line for f prime. So I'm going to go ahead and make a number line. I'm going to label it f prime. Okay, so, yes?
We didn't get a paper like the graph.
All right, so we have this original graph of f of x. The first thing we want to do is we want to make a number line for f prime, right? Because really, to look at a graph and to make a graph of the derivative is a tall order, but a number line is really straightforward here. So if we look, for this graph, we want to think about where the tangent lines would be positive. And so here, as we look, we can see the tangent line's positive, all the way to the bottom of the graph, and then up to here. And then somewhere in here, we have a horizontal tangent, correct? So wherever we see the horizontal tangent, that means that f prime is equal to 0, right? So what would we get for that one? I estimated that was at about 1.5, -1.5. So on this number line, I'm going to go ahead and put a dash at -1.5. Now, to the left of that, we said the slope of the tangent lines were positive, correct? So I just put a plus there. It tells me that from -infinity to -1.5, right, that f prime will be positive. Right? I know that f prime is positive, right, because it was increasing here, right? The slopes of the tangent lines would be positive. What's our next horizontal tangent? Would be here at 0. It's more 0 on the paper than on my graph, but we'll have it at 0. And from this maximum to this minimum, we see that it has a negative slope, correct? So I'm going to go ahead and put a negative here. And then from 0 to infinity, we see that it has a positive slope again. So guess what we put? Positive. Right? So that is a number line for f prime. Now, using this, we can sketch a potential graph for f prime. Like with this, the x values are going to stay constant. We're not going to worry much about the y values. All we care is it above or is it below. So I wouldn't even bother scaling the x-axis or the y-axis at all. But in order to graph this one, we have, let's see, if this is -2 and this is -1, and that's 1. We have a 0 here at -1.5 and at 0. Over here it's positive. Again, this is the graph. I'm going to label that as y equals f prime of x. Labels are very important here. Right? If we don't label things, we're not going to be able to know what we're referring to. And so we said here it's positive, here it's negative, here it's positive. What type of graph do you think this is going to be? Any ideas? That looks a lot like a cubic, doesn't it? What's the derivative of a cubic? Quadratic, right? It's going to be parabola. It's just so it's going to look something like that. Now, could it be flatter? Could it be steeper? We don't know. But this is what we did. This is showing us that from -infinity to -1.5, it's above the x-axis. From -1.5 to 0, it's below. And to the right of 0, it's above. That seem reasonable? Just using that information. Now, for the number line for f double prime, we can use this graph and we can make some educated guesses. Kind of have to do that. We know that these two, so if we look at this graph of f prime, we see that it does have a horizontal tangent here, correct? I would think a safe bet would be to say it's halfway between these two, right? It hit here at negative 1.5, it hit at 0. It's reasonable to assume that the horizontal tangent would be at negative 0.75. So I'm going to go ahead and say negative 0.75. Now, as we approach from the left, so if we're talking about f double prime, we go back to the graph of f prime and talk about its slope, right? So to the left of the minimum, it has a negative slope, correct? So this will give us a negative. And then it hits the minimum, which we thought was about at negative 0.75. And then it has a positive slope. So that would be a number line for f double prime. Now, we built it using the graph, but what this would tell us is so to kind of put everything back together with our curve sketching information, is we built this one by doing increasing and decreasing. But if we look, this tells us that if we go back to f, the original function, that from negative infinity to negative 0.75, because f double prime is negative, it should be concave down. If we look, that appears to be concave down, right? At some point here, the concavity switches. And that would be, we estimated at negative 0.75 to infinity, it's going to be concave up, which is this piece right here. The one thing that we did not put in our table, but I can mention it, is this point here, when f double prime changes signs, is called a point of inflection. It's where it switches from concave up to concave down. Called a point of inflection. So here, we'll talk more about that, but a point of inflection. So f has a point of inflection at x equals negative 0.75. Does that seem clear-ish? Okay, so let's look at our second example here. We're doing the same thing. We're going to make a number line for f prime, and then we're going to sketch f prime, and then we're going to make a number line for f double prime. So we're looking at f, the original function. So remember, to go like from a function to its derivative, don't look at the zeros over here. They'll distract you. Look at the horizontal tangents. Horizontal tangents are what you're looking for. So as we look at this, and my graph is probably close, but not probably very accurate. On the better graph here, we see there's this horizontal tangent here would be at 4, negative. So negative 4. Then there appears to be a horizontal tangent at 1. And then there's a horizontal tangent at 2. Yep. Now, if there's a horizontal tangent, especially if there's a min, a max, and a min, we know it's changing slope, right? So over here, to the left of negative 4 is a negative slope. Between negative 4 and negative 1, which I put 1, it should have been negative 1, is a positive slope. And then from negative 1 to 2, which again my graph is lacking a bit, will be a negative slope. And then from 2 to infinity is a positive slope. I think we all had that. Okay, so then our graph of y equals f prime of x, again, don't skimp on the labels. The labels will help you a bunch. Is we see that there are going to be zeros at negative 4, negative 1, and at 2. Okay. And we see that the function is negative, positive, negative, positive. So just kind of a good old cubic function. Looks like that, basically. Now it's nice when you're working with polynomials, as you know kind of what they're going to look like. As the functions get tougher, it's not the case. So we want to fall back on good technique. And then from here, we're going to make a number line for f double prime. Okay, so again, we're taking the derivative of a graph, we're going to put it onto a number line, so we're looking for horizontal tangents. We have a horizontal tangent here and I just went halfway between -1 and -4, just averaged them. I got -2.5. Again, you could write a function where it's not exactly there, but from the information we're given, I think that's the best guess. It's just to average them. And then here between -1 and 2, we also have a horizontal tangent. So that would give us 0.5 if you averaged them. And then as we approach this maximum, we have a positive slope. So we'll get a plus there. And then from here to here, we have a negative slope. And then to the right of 1, we have a positive slope. So this tells us about the concavity of the original graph. So if we go back to the original graph, from -∞ to -2.5, which was about here, it appears to be concave up. That seems pretty believable, right? At -2.5, the concavity changes. That's what it tells us here. Right? And it appears to stay concave down until about 0.5, reasonable. Then it changes and it's concave up. Okay, so that's how we can investigate a function graphically. But again, it's really important to realize, am I looking at f, am I looking at f prime, and all that good stuff. Okay, so this is our third example from the worksheet here, and I tried the best I could to get this graph. Again, the scale on your paper is a little better. But here we're given a graph of y equals f prime of x. So we don't actually know what the original function looks like. And really with the information we're going to get, we're never going to know exactly what it looks like, but we're going to have some possibilities. That's more later to come in this course. So the first thing it asks us to do is to draw a number line for f prime. Now, we have a graph for f prime already. So if I'm going to draw a number line for f prime, I don't want to think about horizontal tangents. I just want to think about zeros. Where is it positive? Where is it negative? So looking at this, I see that it has a 0 at -2, maybe -0.75, and 0.5. Or well, I had 1 on my paper. I think it is 0.5, isn't it? Whoops. So, all right. So we have that. If you check the key, I'm going to have 1 written there because this is the key. But so we okay there? We were just identifying these are just the 3 zeros of the graph, right? The x-intercepts. And then we're not talking about slope because we're just talking about the function itself. This function is negative to the left of -2. It's positive here, so we'll put negative. It's positive between -2 and -0.75. It is negative here, and it's positive here. Okay, so just to be careful, it's a different process there. The next thing we're asked for is to draw a number line for f double prime. So because we have a picture of f prime, to get f double prime, this number line is going to have zeros where there's horizontal tangents on f prime. Does that follow for everybody? It's like when you go like one derivative down, you look for horizontal tangents. That's how I think of it. So I approximated this was at about -1.5. And then I well, this one's at 0. It looks like pretty definitively. So sometimes I try to get all cute and like line the number lines up. Because why not, you know? But if I look, if these are the 2 horizontal tangents, right, I can see that the slope of the tangent line to the left here is positive, right? And then negative, and then positive. Like so. Now, what we're going to do now is we want to talk about f, right? So the next question is, and this is why there's not a ton of room on this worksheet, but the next question is, where is f increasing or decreasing? We can't, on the other side of the paper, we could just look at the graph and be like, oh look, it's increasing, oh look, it's decreasing. Now we can't, we have to go back and use our properties that we talked about to start the video off here. So we would say f is increasing. Again, don't say it is increasing. You can see the problem there, right? We're talking about three different functions in this problem. But f, the original function, is increasing. So remember, increasing is when the derivative is positive, correct? So that would be when f prime is positive. So I'm going to go to my f prime number line. It's positive from -2 to -0.75, and from 0.5 to infinity. And I'm going to go ahead and say that's because f prime is greater than 0. Okay, so the original function is increasing because f prime is greater than 0. If you have these endpoints for increasing and decreasing, you technically do use a bracket. If you use a parenthesis, I'm not going to count off for that, but it is technically a bracket. Now, we talked earlier, f is decreasing when f prime is less than 0, right? Less than 0. So that would be, I'm just going to look at my number line, and it's much easier, I think, to look at the number line to tell when it's negative than to try to figure out, go back to the graph and try to figure out what's going on. I mean, you could, negative here, negative there, but we would get from -infinity to -2, union, -0.75 to 0.5, because f prime is less than 0. We good there? Now the next question asks about minimums and maximums. Okay, where, and when it says where, it means what x value. Don't, if it says where's the minimum, don't say, well, that's where it goes up and it turns, it goes down. Like, where, location. So let's say f has a maximum, and this will be a local max, at, well, let's see, that would be where the original function would be increasing and then it would start decreasing, right? That's a maximum. So it's when it goes, when f prime goes from positive to negative. So where does f prime go from positive to negative? Well, that would be at -0.75. Okay. And that's because f prime goes from positive to negative. Maybe just a kind of a little shorthand there, right? And then f has a local min at, there's actually two of them, and then that's going to be where it goes, where f prime goes from negative to positive, right? So that would be at x equals -2 and at x equals 0.5, and that's because f prime goes from negative to positive. Does that work for everybody there? Again, that was our definition, right? We know that f prime tells us about the slope of the original function f. So if f is increasing to decreasing, we have a max, or the f prime is positive to negative, and the same thing. And the same case with the minimum. And then let's see, what's our next question? State the intervals where the graph of f will be concave up or concave down. So we know concave up and concave down is based on the second derivative, which we have this number line. So we would say f is concave up, CCU, usually what we put. And with these, you're going to do the intervals, and actually you just use parentheses on these. Again, not going to be that picky, but it would be, so -infinity to -1.5, and then from 0 to infinity. And then f is concave down from -1.5 to 0. Is it looking okay so far? We okay with these facts? Okay, our last thing we want to do is draw a possible graph of f of x. There are actually infinite number of graphs that would match these conditions. We just want to graph one of them, right? So to do this, this is going to be the graph of y equals f of x. And what you want to do here, really, kind of the easiest way, is look at your mins and your maxes, kind of figure out where they're at, and then just kind of draw a curve from there would be what you want to do. So we know that we have a local, well here, I guess I could put a scale on here, huh? Now, I usually tend to draw them where the maxes are like above the x-axis and the mins are below, but this whole graph could be shifted up and down. It's just a general shape is all this is. But I think it's kind of easier to draw them this way at times. So there's a local max at negative 0.75. No, we don't know, we don't have enough information to know what the y value is. So I just know there's some point that's going to be a high point at negative 0.75. There's a local min at negative 2. Okay, there's a point, what's got to be lower than the max, right? So I'm going to have a point somewhere at negative 2. Doesn't have to be below the x-axis. I think sometimes it makes more sense mentally to do that, but we realize we can shift it. And then there's also a local minimum at 0.5. So maybe over here. Right. Now, this is a min, this is a max, this is a min. We kind of expect this, don't we? And if we look, does that agree with the first derivative, which says it's decreasing to negative 2, it's increasing to negative 0.75, it's decreasing, it's increasing. So one potential graph could be that, something that looks like that. Now, it would be every bit as valid and every bit as correct if you'd have said, well, I want to put my maximum right here, and I want to put a minimum over here, and I want to put a minimum here. This would also meet our requirements, this purple graph. It could look like. Would that also meet our requirements? Sure. So again, there's not going to be one graph, but they're all going to have a very similar shape is what we want to do there. All right, so there we go. I think that was all the questions it had there.